Let's consider the following situation. Suppose we have a system of linear equations, but no right-hand side. And we are playing the following game. So we just take our x values and plug them into each equation of the system. So this will produce one right-hand side for each value of x's. What sort of operation this becomes? So here what we have is two ingredients. So the first ingredient is we have a matrix of the size m by n. And then we take and we plug in a vector with n components. And so this is our input. And the output of this operation is another vector, but now with m components. So now we can view this as an operation of multiplication of a matrix and a vector. And the output of this operation is, again, a vector, possibly with a different number of components. This operation is called multiplication of a vector by a matrix. And so the way how we write it is we write a matrix, times a vector, so it could be x or v, right? And the result is going to be another vector w. So here A is an m by n matrix. So V is a vector with n components. And so this is input. And W is our output, is a vector with m components. Of course, instead of doing this over real numbers, we can also do it over an arbitrary field. Let us look at the rule how we calculate the product of a matrix with a vector in more detail. So if W is the product of A with V, then component number I of W is, well, so how do we calculate component number I? So component number I comes from the ith row of this system of equations. And what we see is that the left-hand side here is nothing but a dot product, right? So this is a dot product of our vector V with ith row of the matrix A. So what we can do is we can say that component number I of the output is the dot product of row number I of A with vector V, right? So the row number I of A is, again, a vector with n components, and V is a vector with n components. So when we take the dot product, we get a number. And this number is component number I of the output here. Let's do a quick example. Let's multiply this matrix by this vector. This matrix is a 2 by 3 matrix. So it has 2 rows and 3 columns. And we multiply it by a vector with 3 components. Right? And so what this tells us is that the output of this operation is going to be a vector with 2 components. So how do we calculate those components? So we take rows of this matrix and we compute dot products of each row with this vector. So for example, here we take the first row and take the dot product of 1, 2, 3 with 2, 1, 5. So this dot product is going to be 1 times 2. 1 times 2 plus 2 times 1 plus 3 times 5. So this is 2 plus 2 plus 15. So this is 19. And so then we take the second row. So the second row will give us the second component of this vector. So we get 4 times 2 plus 5 times 1 plus 6 times 5. So here we have 8 plus 5 plus 30. So that's going to be 43. So here, so this is an example of how we multiply a matrix by a vector. Now let us expand this example. I'm taking the same matrix, but now I will write the vector in a general form. I'll write down S1, S2, and S3. Now, let's multiply this vector by this matrix. Well, we still have dot products. So here we're going to get 1 times S1 plus 2 times S2 plus 3 times S3. And the second component of this vector is going to be 4 times S1 plus 5 times S2 plus 6 times S3. So now I'm going to do the same trick as we did when we were looking for general parametric solutions in a vector form. I'm going to take this vector and split it as a sum. So this can be written as a sum of 3 vectors. So it's going to be S1 for S1 plus 2S1, 2S2, 5S2 plus 3S3, 6S3. And finally, I'm going to pull out the S coefficient in front. So this is going to be S1 times 1, 4 plus S2 times 2, 5 plus S3 times 3, 6. Now, what we've got here is a linear combination of 3 vectors, 1, 4, 2, 5, and 3, 6. What are these vectors? So we can see that these vectors are nothing but the columns in this matrix. So here what we see is that the product of this matrix with the vector is a linear combination of the columns of this matrix. So let's record this, that the product of a matrix A with vector V, which is S1 dot dot Sn, is a linear combination of columns of A. And so this is going to be S1 times column 1 plus S2 times column 2 plus Sn times column n. Now, what we see here is that we have 2 descriptions of the product of a matrix with a vector, or maybe 3. So the first one is by means of a substitution, right? So we think that we are substituting values of unknowns into the left-hand side of a system of linear equations. The second interpretation is in terms of rows of matrix A. And we say that the ith component of the output is the dot product of row number I of A with the input vector V. And the third interpretation is in terms of columns of A. So what we're saying is that the product of a matrix A with a vector V is a linear combination of columns of A with coefficients that come from the components of the vector V. This discussion leads us to 3 ways to view a system of linear equations. So the first way is the standard way, the one that we started with. So we have a system of linear equations. So we have m equations with n unknowns. So this is the first way of looking at the system of linear equations. So the second way is as a product. So here we form a matrix A, and we have the vector of unknowns x. And we multiply a matrix by a vector, and what we get is we get a vector of right-hand sides. And now we can think of a system of linear equations in terms of a product of a matrix with a vector. And so here we're solving the problem of finding a vector such that when we multiply this vector by a given matrix, we get the given vector in the right-hand side. So we see that these two problems are totally equivalent, so we just write them in a different way. And there is a third way. And the third way is as a vector equation. So as we said, that the product of a vector with a matrix can be interpreted as a linear combination of the columns of the matrix A. And so if we treat columns of the matrix of A as vectors, then we get the following equation. So x1 times column 1 plus x2 times column 2 plus xn times column n. And the result must be a right-hand side column B. And so what we see is that we have three different levels here. One level is the level of numbers. So here we look at equalities of numbers here. The second level is the level of vectors. So here we look at an equation with vectors. And the third way is the level of matrices. So here we just look at the product, single product of a single matrix by a single vector, and the result is a new given vector. All these three ways to look at a system of linear equations are useful, and each is used in maybe a different context. And it's important to keep all three of them in mind and be able to go from one outlook to another. Right? And sometimes you may start here and go to, say, a conventional system of linear equations. Or sometimes you have to do something else. Right? So you have a conventional system of equations, and then you want to operate with it purely algebraically in a very compact form. Let us look at the following problem. So we need to answer the question, does a given vector from R4 belong to the span of three vectors v1, v2, v3, where v1, v2, and v3 are given here? So what we have here is we have three vectors in R4, and we take their span. So this will be a subspace inside R4. And the question is whether the vector w belongs to this subspace or not. Now, how can we decide? So we have to recall the definition of the span. The span is the set of all possible linear combinations of v1, v2, and v3. So the question is, so can a linear combination of these three vectors be equal to the vector w? In other words, is it possible to find the values of x1, x2, and x3 such that a linear combination x1 times v1 plus x2 times v2 plus x3 times v3 is equal to w? So here, the left-hand side is the description of arbitrary linear combinations of v1, v2, v3, that is vectors in this span, and the right-hand side is the given vector w. And the question is, can we solve this equation? And this equation is a vector equation. So this equation is exactly of the type that's given here. So here we are given 3 vectors and the 4th vector in the right-hand side. And we need to find unknowns such that this linear combination of these 3 vectors is equal to a given vector w. So what we see is that then this problem becomes equivalent to a system of linear equations. And what is the matrix of this system of equations? Well, the matrix is such that these given vectors are columns of this matrix. So in this formulation, we are not given the matrix. And the point is that we need to construct this matrix. And this rule tells us how this matrix is to be constructed. So this matrix is to be constructed by taking given vectors as columns. So let us record this mantra. When solving vector equations, form a matrix by placing given vectors as columns. Right? So this means that we take this vector equation, we interpret these vectors as columns, and we get a vector equation that corresponds to a system of linear equations. And then we form matrix A by taking given vectors as columns. So if we follow this rule, then we take these 3 vectors and place them as columns. So this will give us a coefficient matrix. Right? So this will be matrix A. And so here we have the right-hand side column. Well, this becomes the part of augmented matrix. So we put 3, 0, negative 4, 1. And now what we've got is we've got an augmented matrix of a system of linear equations. And so now we get the familiar problem of solving a system of linear equations. And we see that now we've got interpretation of this problem with vectors. So essentially a vector equation. We interpreted it back as the problem of solving a system of linear equations where we already developed methods like Gaussian eliminations to solve such a system. So what's the meaning of this question in the language of systems of linear equations? So here we are asking whether a vector belongs to the span of the given 3 vectors. In other words, whether this vector equation is solvable. So are there unknowns, values of unknowns x1, x2, x3 that give us equality? And then this clearly becomes equivalent to the question, so is a system of linear equations that we've got ax equals w consistent? So if the system of linear equations has a solution, so then we get a positive answer to our question of this existence of solution to this vector equation. And if the system is inconsistent, then the answer to this question about the span is negative. All right, so since we haven't done this for a while, let's practice and solve this system of linear equations. So here we have the first step. We need to create a pivot 1 in the top left corner. So we could have been dividing by 2, but I would rather use this -1 and create a pivot out of it. So what I'm going to do is I'm going to swap first row 1 with row 3. So then the new matrix is going to be -1, 3, 0, -4, 0, 2, 1, 0, 2, 1, 1, 3, 3, 4, 1, 1. So then the next step is I'm going to multiply the first row by -1. So then the matrix becomes 1, 3, 1, -3, 0, 4, 0, 2, 1, 0, 2, 1, 1, 3, 3, 4, 1, 1. Now we've got a pivot in the top left corner, and we need to eliminate entries in the first column below the pivot. So we can, in the second row, we already have a 0. So what we need to do is we need to take new row 3 is row 3 minus 2 times row 1, and new row 4 is row 4 minus 3 times row 1. So we get the following matrix. So the first row is unchanged, 1, -3, 0, 4. So the second row is unchanged, 0, 2, 1, 0. Then in the third row, we get 2 minus 2, that's 0. 1 minus -6, that's 7. Then 1 minus 0, that's 1. 3 minus 8, that's -5. And in the last row, we have 3 minus 3, that's 0. 4 minus -9. So that's 4 plus 9, that's 13. And 1 minus 0 is 1. And 1 minus 12, so 1 minus 12 is -11. Now, so with this matrix, I want to create a pivot here. And what I can do is I can say that row 2 new is 1/2 of row 2. So we can multiply the second row by 1/2. And we get the matrix 1 minus 3, 0, 4, 0, 1, 1/2, 0, 0, 7, 1, -5, and 0, 13, 1, -11. So here we've got our second pivot, and we eliminate entries underneath. So we say row 3 new is row 3 minus 7 row 2, and row 4 new is row 4 minus 13 row 2. So this gives us the matrix 1 minus 3, 0, 4, 0, 1, 1/2, 0. Then we subtract 7 times row 2. So we get 0 here. So we have 1 minus 7/2. So that's -5/2. And here we get -5. And in the last row, we have 0, 0. So then 1 minus 13/2. That's minus 11/2. And we have minus 11 in the right-hand side. So this is the matrix. So now we say, so we can create a pivot here. So we say row 3 new is -2/5 of row 3. So we multiply row 3 by -2/5. So we get the matrix 1 minus 3, 0, 4, 0, 1, 1/2, 0, then 0, 0. So this will become a pivot 1. And -5 times -2/5, that's 2. And the last row is 0, 0, minus 11 halves, and minus 11. And now to bring this matrix to row echelon form, so we just do one more step, and we say row 4 prime is row 4 plus 11 over 2 times row 3. And this will eliminate the last row of a matrix, and we get 1 minus 3, 0, 4, 0, 1, 1 half, 0, 0, 1, 0, 0, 1, 2, and 0, 0, 0, 0. Now let us bring this to reduced row echelon form. So now we need to eliminate this 1 half. So we say that row 2 prime is row 2 minus 1 half row 3. So then the new matrix is 1, negative 3, 0, 4, 0, 1, 0, and then 0 minus 1 half of 2. So that's minus 1, and 0, 0, 1, 2, 0, 0, 0, 0. And now the last step. So we say that new row 1 is row 1 plus 3 times row 2. We get 1, 0, 0, 4 plus negative 1, that's 3, 0, 1, 0, negative 1, 0, 0, 1, 2, and all zeros here. So what we see is that now we have reduced row echelon form, and all pivots are in the coefficient matrix. So we have no pivot in right-hand side column. So this means that the system is consistent. So we don't have an equation with a 0 in the left-hand side and non-zero constant in the right-hand side. And so from here, we read out the values of our unknowns. So in this case, we have no free variables. So every variable is a leading variable. So there is a unique solution. So we get that x1 is equal to 3, then x2 is equal to negative 1, and x3 is equal to 2. And what this means is that indeed W is a linear combination of V1, V2, and V3. So what we get is that W is 3 times V1 minus V2 plus 2 times V3. So this shows us how to expand W as a linear combination of V1, V2, and V3. And since W is a linear combination of these three vectors, so this means that the answer to this question is positive. So this vector indeed belongs to the subspace spanned by the given three vectors. And so here we've got explicit linear combination that tells us how this is done. When solving problems like this one, it's always a good idea to go and check your answer, right? So here we can just take vector v1 multiplied by 3, subtract v2, and add 2 times v3. And so it's a good idea to verify that the result will be exactly the vector w. Let us introduce 3 subspaces that are associated with the matrix. So let A be an m by n matrix with entries in a field F. So this means that this matrix has m rows, and each row has n components. So the first subspace is the row space of A. So this is a subspace of Fn spanned by the rows of A. So as we said, each row has n components, so this means that rows can be viewed as vectors from Fn. So the second subspace is the column space of A. So this is, so remember that each column now has m components. So this means that this is a subspace of F, now m, spanned by columns of A. And the third important subspace is the null space. So null space of A is the set of solutions of equation AX equals 0. So when we talked about subspaces, we said that the set of solutions of this equation is always a subspace. And this is a subspace so for m by n matrix A, X must have n components. So this means that this is a subspace of Fn. So what we see is that the row space and the null space, these are two subspaces in the same space. And if the matrix is not square, then the column space is a subspace in a different space Fm. Let us state the following theorem. A system AX equals B is consistent if and only if B belongs to the column space of A. Right. So we see that so B is a vector that has m components, so it lives in the space Fm, and the column space is a subspace in Fm. And now, so what we say is that this system is consistent when this given right-hand side vector belongs to the subspace spanned by the columns. And so the proof of this relies on our three different ways of interpreting a system of linear equations. So what we see is that AX equals B may be written as a vector equation. So x1 times c1 plus x2 times second column of A plus xn times the last column of A, and is equal to B. And so now, so this system is consistent if we can express B as a linear combination of the columns. So this tells us that AX equals B is consistent if and only if B is a linear combination of columns of A, and this happens precisely when B belongs to the column space of A, because the column space of A is exactly the set of all possible linear combinations of the columns. And we prove this theorem. And let's state another theorem that says null space of A consists of vectors in Fn which are orthogonal or equivalently have zero dot product with every vector in the row space of A. So this means that vectors in the null space of A are orthogonal to vectors in the row space of A. And the null space consists of precisely all vectors in Fn that have zero dot product with every vector in the row space of A. Let's prove this theorem. So by definition, a vector v in Fn belongs to null space of A if and only if the product A times V is equal to the zero vector. So this is the definition of the null space. But how do we calculate the product of a matrix with a vector? So this was one of our rules. So we see that component number I of the product AV is the dot product of row number I, so dot product with V. And so what we see is that this product of a matrix with a vector is equal to 0 if and only if, so let's write it down. So AV is equal to 0 if and only if for all I, the dot product of Ri with V is equal to 0. So here we use dot product. And what we see is that this tells us that the vector V is orthogonal to every row of the matrix. And here, and vice versa. So if V is orthogonal or has zero dot product with every row of the matrix, then it belongs to the null space. And now what we need to see is something stronger, that if V has zero dot product with every row, then it has a zero dot product with any linear combination of the rows. So we recall that the row space is the set of linear combinations of rows of A. So what remains to prove? So what we need to show is the following fact, that the claim that a certain vector has dot product 0 with every row of a matrix is equivalent to saying that for every vector W in row space of A, we have W dot product with V is equal to 0. So in one direction, so this is clear, right? So here, suppose for every W in row space of A, W dot V is equal to 0. So then we know that each row belongs to the row space of A, because a row is a linear combination of the rows. So we just take this row with coefficient 1 and all other rows with coefficient 0. So if we know that for every vector in the row space of A, this dot product is 0, so this implies that for every I, row I dot product with V is equal to 0 as well. And so this equivalence is proved in one direction. Now we need to prove this in the other direction. So suppose for every I, row I dot V is equal to 0. Now let us take W in row space of A. So the row space of A is the set of all possible linear combinations of rows of A. So this means that W can be written as S1 row 1 plus Sn, or rather M, row M. And then what is the dot product of W with V? So this is the dot product of S1 R1 plus Sn Rm, Sm Rm, dot product with V. But we know that dot product is bilinear. So this means that this is equal to S1 times R1 dot V plus dot 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 Sm times Rm dot V. But we assumed that the dot product of each row with V is equal to 0. So this means that each term in this sum is equal to 0, and the result is equal to 0. And so what we proved, that if the dot product of V with each row of the matrix is equal to 0, then the dot product of V with every vector in the row space of A is equal to 0. And what we see is that the condition that dot product with each row is equal to 0 is equivalent to the condition that dot product with each vector from the row space is equal to 0. And so here what we said is that this condition AV is equal to 0 is equivalent to saying that the dot product with each row is equal to 0. And now we see that this is equivalent to saying that for all W in row space of A, we have W dot V is equal to 0. And that's exactly the claim of our theorem. Our theorem claims that the set of vectors that are in the null space, so this means that they satisfy AV is equal to 0, is exactly the set of vectors that have 0 dot product with every vector in the row space of A. So this gives us a relation between the row space of A and the null space of A. So they are orthogonal to each other.